Assalamualaikum everyone, this is Sunjida Nova. Today I am going to talk about one of the most fundamental concepts in AC electrical system, real, reactive and apparent power. I will explain what each type of power means, how they behave differently in AC circuits and why all three are critical for the operation of transformers, motors, generators and other power system components. By the end of this session, I aim to show how these powers relate through the power triangle, how they impact power factor, and how they influence the design and performance of the entire power delivery system. Let's begin with real power. Real power, also called active power, is the power that performs actual work in the electrical circuit. For example, it powers a heater to produce heat, lights to bulb produce light, and a motor to generate motion. This power consumed by the load and converted into useful forms of energy. It measured in watts or kilowatts, and it's what your utility company charges you for. Real power is the component of AC power that is actually consumed by the load to perform measurable work, such as generating heat in resistive heaters, producing light in incandescent lamps, or driving mechanical systems in motors. Mathematically, real power can be expressed as P is equal to VI cos phi, where V represents the RMS voltage, I represents the RMS current, phi is the phase angle between voltage and current, cos phi represents the power factor. The unit of real power is watt, which practical system typically using kilowatts or megawatts. In a purely resistive load where voltage and current are in phase, in that case phi is equal to 0 degree. Now I would like to discuss about the key characteristics of real power. It represents the portion of total power that is converted into usable energy. It is the only component of power that results in energy transfer to the load. Real power is monitored for metering purposes and is directly reflected in utility billing in units of kilowatt hour. Therefore, real power is a direct measure of energy consumption in practical AC system. When the load is purely resistive, there is no reactive component, so voltage and current remain in the same phase. In this case, the power factor is 1 and all the supplied power is converted into real work with no energy loss to magnetic or electric fields. In this diagram, we can see that an AC system, voltage and current alternate their direction in 50 or 60 times per second. It is the normal behavior of real power in AC circuits. In an AC system, voltage and current alternate their direction 50 or 60 times per second. Now, when the load is purely resistive, such as a heater or incandescent bulb, the voltage and current are in phase. They rise and fall together. This means that the power flow is always in one direction, from the source to load, and it doesn't return. From this diagram, we can see that the power flows from source to load. So the power is completely consumed and it does useful work. In summary, real power represents the effective energy used by a device to do work and is the backbone of any functional load in an electrical system. What makes real power significant is that it is the power that gets converted into actual energy, the kind we can feel, see or use. In summary, I can say some example, that is a heater converts real power into heat, a bulb converts it into light, a fan uses to produce motion. Because it performs real work, this is the only type of power that utility companies bill consumers for. So when we look at our electricity bill, we see kilowatt hour uses that reflects our real power consumption over time. Here's an example of electric room heater. For example, the voltage is 230 volt, current I is equal to 10 ampere, and as it is purely resistive load, so the power factor cos phi is equal to 1. If we want to calculate the real power, then our equation was P is equal to VI cos phi. By substitute the values, we get P is equal to 2.3 kilowatt or 2300 watt. Here's some interpretation, that is, the heater converts 2.3 kilowatt of electrical energy into heat. Since it's a resistive load, like most heaters, all supplied power is real power. No reactive power is needed here. Real life implementation, if we run this heater for 4 hours, energy consumed P is equal to W is equal to P multiplied by T, that is our time T is equal to 4 hours and the P was 2.3 kilowatt. In that case, our energy consumed 9.2 kilowatt hour. Our electricity bill will be charged based on this 9.2 kilowatt hour. Let's talk about reactive power. Reactive power does not perform real work, meaning it does not produce heat, light, or motion directly. However, it is absolutely essential for operating inductive and capacitive devices such as motors, transformers, and capacitors. These devices need to create and collapse magnetic or electric fields to function. That process requires energy to flow back and forth, which is provided by reactive power. Now I'll discuss reactive power, an important but often misunderstood component of AC power system. Reactive power is the part of total AC power that flows back and forth between the source and the reactive elements in the circuit, especially inductors and capacitors. Unlike real power, it is not converted into heat, light, or mechanical energy. Please note this point. Unlike real power, it is not converted into heat, light, or mechanical work. However, it plays a critical role. Reactive power is essential for establishing and maintaining electric and magnetic fields, which are necessary for the operation of many AC devices such as motors, transformers, and reactors. The formula used to calculate reactive power is Q is equal to VI sin phi. Here V represents the RMS voltage, I is the RMS current, and phi is the phase angle between the voltage and current waveforms. This equation tells us reactive power arises whenever there is a phase difference between current and voltage, which is typical in the system with inductive or capacitive elements. Reactive power is measured in volt amperes reactive, abbreviated as VAR, with typical system values given in kilovolt ampere reactive or megavolt ampere reactive depending on scale. Reactive power does not result in net energy transfer to the load. Instead, it is cyclically exchanged between the source and the reactive components of the system. In an inductive load such as motors or transformers, reactive power is used to maintain the magnetic field. In a capacitive load, it supports the charging and discharging of the electric field. Now, reactive power does not perform real work and it is not billed to residential users. Does this mean reactive power is wasted? Justify your answer with technical reasoning. What do you think? Please take a moment to think about this answer. Does it make sense to you? What are your thoughts on it? Actually, reactive power is not wasted, but it must be managed. Reactive power does not result in net energy transferred to the load that I have discussed earlier. Instead, it is cyclically exchanged between the source and the reactive components of the system. In an inductive load such as motors or transformers, reactive power is used to maintain magnetic field. In a capacitive load, it supports the charging and discharging of electric field. The key characteristics are it does not produce heat, light or motion, hence it does not perform real work. However, it is essential for the functioning of AC machines that rely on time-varying fields. Excessive reactive power can reduce system efficiency and must be managed through compensation techniques, for example, capacitor banks, synchronous condensers, etc. While not built to residential users, reactive power is carefully monitored in utility networks because of its impact on system voltage stability, current levels, and power factor. Reactive power does not perform real work, but it is essential for us. Why it's not wasted? Reactive power is essential in AC system for creating and sustaining magnetic and electric fields which are required to operate motors, transformers, capacitors. Reactive power flows back and forth between the source and the reactive components like inductors or capacitors. It is not consumed, just exchanged cyclically. The average real power of this oscillating exchange is zero, but the energy is needed to enable field-based operation. Even though reactive power isn't wasted in a conventional sense, too much of it causes problems such as increases current in transmission lines, causes I2R loss, which are real power losses, reduces power factor, making the system less efficient, occupies capacity in generators and transformers that could otherwise deliver more real power. That's why utilities actively monitor and control reactive power even if it's not directly billed to residential consumers. Finally, we can say that think of reactive power like pumping motion on a swing. If we don't move forward from pumping alone, but it's necessary to keep the swing moving. Similarly, reactive power is not wasted, but essential support for the movement. Finally, we can conclude that reactive power is not wasted. It is necessary for AC system operation, but too much reactive power can reduce efficiency and increase losses, so it must be controlled. There are some real-life examples of reactive power in inductors such as motors or transformers. It resists changes in current, need magnetic fields maintained by reactive power. Capacitors, it resists changes in voltage, absorb or release energy using reactive power. Here's the example of reactive power. Here we connect a load which is purely reactive. It can be either capacitive or inductive. Let's explain it briefly. The inductors which are used in motors and transformers, inductor resists changes in current to maintain the magnetic field needed for operation. They temporarily absorb energy and they return it to the circuit. This is reactive power. It does not produce heat or light, but it's what allows the magnetic field to be maintained. Now I would like to discuss about the roles of capacitors. It is used for power factor correction or voltage support. Capacitors resist changes in voltage. They store energy in an electric field during part of the cycle and release it during another part. Again, energy flows in and out but is not consumed. This is also reactive power. Unlike real power, reactive power is not consumed. It simply oscillates between the source and the reactive components. From this diagram, we can say that it simply oscillates between the source and the reactive components. So during each AC cycle, some energy flows from the source to load, that is positive power, and then it flows back from the load to the source, that is the negative power. This bidirectional flow supports the magnetic field and electric fields that AC equipment relies on. Reactive power is measured in var volt ampere reactive or kilovolt ampere reactive or megavolt ampere reactive. Now I would like to summarize why reactive power is essential. Even though reactive power does not do real work, it is very much important for the operation of AC system. Without reactive power, motors wouldn't start, transformers wouldn't transfer energy, and capacitors wouldn't regulate voltage. In fact, if we tried to operate an AC system with only real power and no reactive power, most of our infrastructure would fail. Let's talk about apparent power. Apparent power represents the total power supplied by the source to an electrical system. It combines both the real power that performs useful work and the reactive power that supports the magnetic and electric fields necessary for an AC equipment operation. The mathematical expression for apparent power is S is equal to root over P square plus Q square, where P represents the real power, Q represents the reactive power in volt ampere reactive, and S is the apparent power in volt amperes. Alternatively, in simple terms, we can say that S is equal to V times I when power factor is included separately in calculations. The unit of apparent power is volt ampere, with practical system using kilovolt ampere or megavolt ampere. Apparent power reflects the total power demand placed on the system, including both the portion that does work and the portion that supports field interactions. The key characteristics of apparent power is apparent power defines the required capacity of the system source such as generators, transformers, and transmission lines. Apparent power defines the required capacity of the system source such as generators, transformers, and transmission line. Apparent power represents the combined effect of both real power and the reactive power. It determines how much current and voltage the system must handle at any moment. Some of the major components are generators, which produce the power, transformers, which step the voltage up or down, transmission lines, which carry the power, must be rated to handle the entire apparent power, not just the portion that does useful works. For example, if a system has 800 kilowatt of real power and 600 kilovolt ampere reactive or reactive power, in that case our S will be 1000 kilovolt ampere. By using the formula S is equal to root over P square plus Q square, we get the value. The generator and transformer must be rated at least 1000 kilovolt ampere, not just 800 kilowatt. Even though only the real power does work, the system must be designed to deliver the full apparent power to account for the actual current and voltage interaction. Real power is the part that performs the actual calculation or actual work. For example, heat, light, motion. Reactive power does not do work but still causes current to flow. The total current that flows through cables and equipment is determined by the apparent power. So even if real power is less, the current is based on the apparent power and all equipment must be sized for that current to avoid overheating or voltage drops. Therefore, apparent power is a critical design parameter for power system infrastructure as it determines the rating and sizing of electrical components in AC power networks. In summary, we can say that real power defines how much energy is used, apparent power defines how much capacity the equipment must handle. Power system components must be rated for apparent power to safely carry the total electrical load. Let's discuss about the power triangle concept and the explanation. It's very essential visualization tool in AC power system. The power triangle. The power triangle is a graphical representation that helps us understand the relationship between three systems of power in AC circuits. First, we have real power, which is measured in kilowatts. This is the portion of electrical power that is actually consumed by the load to do useful work such as heating, lighting, or driving motors. Secondly, reactive power, which is measured in kilovolt amperes reactive, that is kVAR, kilovolt ampere reactive. This is the power that flows back and forth between the source and the reactive components like inductors and capacitors. It is not consumed, but it is required to maintain electric and magnetic fields essential for the operation of AC equipment. Finally, we have apparent power. Apparent power is measured in kilovolt amperes. This is the total power delivered by the source to load, and it includes both the real and reactive components. Apparent power represents the overall load demand on the system, what the generator and transformer must supply. Visually, these three powers form the sides of a right-angled triangle. The horizontal leg represents the real power or active power. The vertical leg represents the reactive power and the hypotenuse represents the apparent power. Here is a mathematical example when the load is purely resistive. In case of purely resistive load, the active power can be calculated by I square R where the reactance is 0. In case of purely reactive load, the reactive power can be calculated by I square X where the active power I square R is equal to 0. There are some difference between active and reactive power. To summarize, real power is what does the actual work. It is what we pay for and what gives us light, heat and motion. Reactive power does not do work directly, but it is necessary to operate magnetic and electric fields in AC equipment. These two together form apparent power, the total power that must be supplied by generators and handled by transformers. So next time you hear about kilowatt or kVAR, remember, one powers your appliances, the other makes sure they can function at all. Let me conclude by reinforcing the core message of this presentation. Real power measured in kilowatts is the only portion of power that performs actual work. It runs motor, lights, our buildings and powers every load that consumes energy productively. Reactive power is measured in kilovolt ampere reactive. It is not wasted but essential. It sustains the magnetic and electric fields that are fundamental to the operation of AC machines like transformers and induction motors. And finally, the apparent power measured in kilovolt amperes is the vector combination of real and reactive power. It defines the total electrical load that the system must supply and that all equipment must be rated to handle. Together, these three components form the power triangle, a foundational model in power engineering. It not only quantifies the energy flow in a system, but also drives decisions in equipment sizing, power factor correction, grid stability, and energy efficiency. In summary, real power powers the world, reactive power makes AC operation possible, and apparent power determines the true burden of the infrastructure. Thank you so much for your time and attention. If you have any confusion, feel free to ask me.